So today I'd like to tell you about a recent joint work with Tom Ransford and also Wen-Hui. So it's going to be about holomorphic motions, capacity, and conformal welding. So let me just start with the definition of a holomorphic motion. So we consider the open unit disk D in the complex plane. And then a holomorphic motion of a set A. So you take a set A in the Riemann sphere, and then a holomorphic motion is a map from the unit disk product with A valued into the Riemann sphere that satisfies the following properties. So the first property is you want that if you fix Z, then the map as a function of lambda should be holomorphic on the disk. Then if you fix lambda, on the other hand, then the map should be injective on the set A. And then lastly, when lambda is equal to 0, the map should be the identity on A. Okay, so those are the three conditions for a holomorphic motion. So note that there is no assumption on the joint behavior of the function at all. So it's just separately holomorphic in lambda, injective in Z, and then it starts at the identity. So for the rest of the talk, I'm going to use the following notation. So I'm going to denote by H sub lambda the function that takes Z and maps it to H of lambda Z. And then if you consider a subset of A, then you can look at its image under the maps H lambda, which I'm going to denote by E lambda. Okay, so you should think of E lambda as some kind of holomorphic variation of the compact set E, maybe with some time parameter, but the time parameter lambda is complex. It lives on the unit disk. Okay, so what's the original motivation to study such things? Well, it mostly comes from holomorphic dynamics. So holomorphic motions were introduced by Malik, and Sullivan in the 1980s. And mostly this is based on the observation that Julia sets of rational maps often move holomorphically when you vary the coefficients of the maps in a holomorphic way. So maybe I can actually show you an illustration of this. So let me try, okay, so share another window. So can you see this? That's a picture of the Mandelbrot set. Yes, okay. So I don't know if you can see on the right, but so this is a Mandelbrot set. We're gonna come back to this picture and I'll explain everything about it. But if you take a point inside the main cardioid, this component here, and as I move my mouse, then what you see on the right is the corresponding Julia set to that parameter. And then you see that the Julia sets, they sort of vary in some kind of holomorphic way as I move my mouse. So this is illustration of the holomorphic motion. It works if you look at any of those components here. Here you also have this kind of motion of the Julia sets, and then also outside of the Mandelbrot set. In this case, the Julia set is totally disconnected, but it still moves holomorphically. Okay, so let's try to go back to the slides. Okay, so you can see the slides back now? Yep, okay. So as I said, this was the original motivation. And Malik and Sullivan, in their paper, they also proved a result about general holomorphic motions. So as I mentioned, there is no assumption on the joint behavior of the map, right? But Malik and Sullivan surprisingly proved that if you have a holomorphic motion, first of all, thank you. So they proved that if you have a holomorphic motion of a set, then you can always extend it to a holomorphic motion of the closure of the set. And moreover, the map that you get, the extension is jointly continuous in the two variables lambda z, which is really not obvious from the definition that you should expect some joint continuity for the holomorphic motion. And then there was a question at the time, how far can you extend a holomorphic motion? And there was a conjecture of Sullivan and Thurston that every holomorphic motion should extend to a holomorphic motion of the whole sphere. And that was finally proved a few years later in some remarkable work by Słodkowski using techniques of several complex variables. So Słodkowski proved that every holomorphic motion has an extension to the whole Riemann sphere. Okay. All right. So this serves as a motivation to study holomorphic motions of the whole sphere. And this is mostly what we will do today. So here's an actual question that you can ask about holomorphic motion. So suppose you have a function, real valued, defined for compact subsets of the plane, and then you have a holomorphic motion with a whole sphere, and I'm going to assume that it fixes the point at infinity. This is always going to be implicitly assumed today. And then you start with a compact set E. Well, what you can do is you can vary the set E holomorphically using the holomorphic motion, and then try to study the behavior of the function applied to this variation of the set E. So how does this function behave as a function on lambda for lambda in a unit disk? And that's a very general question that was studied extensively in the past. So let me mention a couple of related work. So first of all, for f equals to Hausdorff dimension, there's been a lot of work about the study of that function. Here I name a few people, including Ruel and Astala and Zinsmeister, who studied Hausdorff dimension of limit sets of Fuchsian groups that vary holomorphically. And then also I mentioned some work of Tom Ransford about Hausdorff dimension of Julia sets of certain rational maps. There's also some work that has been done on the study of conformal modulus for doubly connected domains under holomorphic motion. So there's the work of Earl and Mitra, who proved that conformal modulus varies in a real analytic way for doubly connected domains under holomorphic motion. And I also mentioned the work of Stamatzis Pouliasis on variation of condenser capacity under holomorphic motions. Now, holomorphic motion also played a very important role in the work of Astala on distortion of dimension and area under quasiconformal mappings. And as a consequence of the work of Astala, you have the following theorem, which says that if you have a compact set and a holomorphic motion of the sphere, again, fixing infinity, then if you let the sets vary under a holomorphic motion, then the area and the Hausdorff dimension both vary continuously. So here A denote the area, and this is the Hausdorff dimension of the set E lambda. So the work I would like to talk about today is is there a similar result for two other quantities defined on compact sets, namely logarithmic capacity and also the so-called analytic capacity. Okay? Questions so far? No? Okay, so let's start with logarithmic capacity, the first result that we have. So first of all, what's the definition? There's a lot of equivalent definitions of logarithmic capacity, but here is one. So you take a compact set E, and then what you want to do is you want to look at the energy of a measure, a probability measure supported on the set, and then you want to minimize the logarithmic energy, take the negative of that, and then you take the exponential. So that is what we call the logarithmic capacity of a set. It's an important notion in potential theory. And now I can state the first result that we have about continuity of logarithmic capacity. So if you start with a compact set and you look at a holomorphic motion of the whole sphere, then the logarithmic capacity varies continuously. So we actually prove something slightly stronger, that the log of the logarithmic capacity is a continuous subharmonic function on the unit disk. Okay. So let me maybe mention that the subharmonic part is not new. It actually follows from a result of Yamaguchi, a more general result on behavior of logarithmic capacity under something called analytic multifunction, which is a generalization of holomorphic motion. But the proof that we gave is different in the setting of holomorphic motions, and it gives, for holomorphic motions, the continuity that we wanted. Also, I'm not going to talk much about the proof of that result because I want to spend more time on the other result. But the proof is based on the characterization of logarithmic capacity in terms of transfinite diameter. So the idea is you can use transfinite diameter to prove that this function, the log of the logarithmic capacity, is a decreasing limit of functions that are pointwise supremum of harmonic functions, and such functions are always continuous. So that's how you get that the function is subharmonic and continuous. Okay. All right. So now let's move on to the other subject today that I want to talk about, analytic capacity. So first of all, what is analytic capacity? So we start with a compact set E in the plane. And then what you want to do, so it's an external problem, you want to maximize the derivative of the function at infinity, where function is holomorphic outside the set with values in the unit disk, so bounded by 1 in modulus. And then the derivative at infinity is this limit here, which is also equal to the coefficient of 1 over z in the expansion of f, of the function g around the point infinity. Okay, so that's the definition of analytic capacity. So it was first considered by authors a long time ago for the study of a problem due to Painlevé. So Painlevé's problem was about finding a geometric characterization of the compact sets that are removable for bounded holomorphic functions. And it turns out that such compact sets coincide with sets of zero analytic capacity. So that's why this external problem was introduced by authors to try to characterize these removable sets, so just the sets of zero analytic capacity. But it turned out to be a very difficult problem. It took more than 100 years until a reasonable solution was obtained due to the work of Tulsa and a lot of other people. Okay, I also mentioned that it's a fundamental tool in the theory of rational approximation of holomorphic functions. This is because of the work of Vitushkin in the 1960s. And then actually, we're not going to need much about analytic capacity today, except that it is closely related to one-dimensional Hausdorff measure. So the relationship is the following. There's an old theorem, usually attributed to Painlevé, which says that if the length is zero, the one-dimensional Hausdorff measure of the set is zero, then the analytic capacity is zero as well. And the converse is false in general, but it does hold provided the set is contained in some nice curve, a rectifiable curve, for instance, a smooth curve. Okay? So just keep that in mind for subsets of a rectifiable curve. One-dimensional Hausdorff measure 0 is the same as analytic capacity 0. And this is really all that we're going to need today about analytic capacity. Okay, so how do you study the analytic capacity of a set under a holomorphic motion? Well, we were able to prove the following result. So it's a negative result. So we showed that there exists a compact set E in a holomorphic motion, again fixing infinity, for which the analytic capacity does not vary continuously. So that's a negative result that you can compare with the positive result for logarithmic capacity. And this result is actually, you can think of it as a supplement to an earlier result that we proved together with Stamatis. So we showed that there exists E and H for which the function's capacity and also the logarithm of the analytic capacity are not subharmonic and also not superharmonic. Okay. So that's a related earlier result. So now I would like to say a few words about how you can prove such a result. So where is, okay, sorry, I got a Zoom upgrade. So yeah, I want to say a few words about how you can construct such a holomorphic motion in such a compact set. So the main difficulty here is that analytic capacity for a given set is in general very hard to calculate or even estimate. But we have this relationship here for subsets of rectifiable curves. So we know that sets of capacity 0 coincide with sets of one-dimensional Hausdorff measure 0. So the idea is to try to construct a holomorphic motion that somehow fixes or preserves some rectifiable curve, let's say the unit circle. So that's what we're going to do. So that's the strategy. So we're going to construct a holomorphic motion of the sphere together with a compact set E and also a sequence of small positive numbers converging to 0 with the following property. So the first property is that my holomorphic motion is going to preserve the unit circle. So the set E will be constructed to live on the unit circle. And then when you apply these h lambda, at least for these values of lambda n, you get a set that also lives in the unit circle. And then the second condition, so I'm going to construct the map h lambda n to satisfy the following properties. So I want the measure, the normalized Lebesgue measure of the set E to be positive on the circle, but whenever you apply any of those maps h lambda n, you get a set that has 0 Lebesgue measure. And then because we have sets that live on the unit circle, then this implies that the analytic capacity of these sets E lambda n is going to be 0 for all n, but the analytic capacity of the original set will be positive. And then the function cannot be continuous, obviously, because you have a sequence of points at which the function is 0 that converge to a point where the function is positive. So that's the strategy. And now how do we construct these maps h lambda? Well, I'm going to construct the maps, the holomorphic motion, so that the restriction of each h lambda to the unit circle is what we call a conformal welding. It will be the conformal welding homomorphism of some quasicircle Julia sets. So obviously I need to explain what this all means. I'm going to do this very soon. But first let me mention, in addition, that the condition here that the measure of the set E is positive, but the image of E under h lambda n has 0 measure, it's some sort of singular condition with respect to Lebesgue measure. So just, I know it's very abstract right now, but just keep that in mind. We're trying to construct conformal welding homomorphisms that are singular with respect to Lebesgue measure in the circle. Okay? And then we want to obtain these conformal weldings as part of some holomorphic motion. So let's focus on the beginning. So let's talk a little bit about conformal welding. So what is conformal welding? We start with a Jordan curve gamma in the complex plane C. And then the curve separates the sphere into two components, which I'm going to denote by omega and omega star. So omega will be the bounded complementary component of the curve, and then omega star is the unbounded component. Then these domains are simply connected, so we can find conformal maps from the unit disk to the interior and also the exterior of the unit disk to the exterior of the curve. So the picture is the following. So here you have the unit disk. It's mapped conformally to the interior component of the curve. And then you have the exterior of the closed unit disk, which is mapped conformally onto the exterior component of the Jordan curve gamma. So here by conformal, I mean analytic bijection, so by holomorphism. Okay, so what is conformal welding now? Well, there is a classical extension theorem due to Caratio-Delhi, which tells us that these conformal maps, they extend to homomorphisms on the boundary of their respective domain. So what you can do is you can start with a point on the unit circle, then you can apply, let's say, the map G, so you get somewhere on the curve, and then you can apply the inverse of F to get back to the unit circle. So this gives you a homomorphism from the unit circle onto itself, and this is what we call the conformal welding of the curve gamma. Okay? Conformal welding is not unique in general because there are some normalizations that you can do for F and G, but I'm still going to denote this by D conformal welding up to some normalization if you want. Okay, so that's the notion of conformal welding. So now what we want to do, recall from the strategy, we want to construct conformal weldings that are singular with respect to Lebesgue measure. So let me explain how you can do this. And this turns out to be related to the harmonic measure with respect to the interior and the exterior of the curve gamma. So first of all, what is harmonic measure? So let's start with a domain in the plane. So you probably need some assumptions on the domain, but I'm not going to bother with that. So the harmonic measure, there's a lot of definitions for it, but one definition that is simple to state is the probabilistic interpretation of harmonic measure. So harmonic measure for a domain omega with respect to some fixed point z in the domain is a probability measure defined on the boundary of the domain in the following way. So if you start with a subset E of the boundary, then the harmonic measure of E is the probability that if you start a Brownian motion at the point Z, and then you let the Brownian motion run all the way until it hits the boundary, well, it's a probability that it hits the boundary at a point of the set E. So that's roughly the definition of harmonic measure in terms of Brownian motion. And now what we're going to need actually is a very simple case where you have a Jordan domain. Well, in this case, if you have a Jordan domain, then the harmonic measure is just the pullback of measure of normalized Lebesgue measure on the circle under a conformal map from the disk to the Jordan domain omega. So here you need to put some normalization on F, but don't bother too much about this. Okay, so this is just roughly conformal invariance of Brownian motion if you want it. Okay, so what's the relationship between harmonic measure and these singular conformal weldings? So again, the picture is the following, and then the conformal welding is this map. So you apply G and then you go back with F inverse. So the observation I want to make is that if you look at the two harmonic measures from both sides of the domain, well, one way to get a singular conformal welding is to make sure that these two harmonic measures from the inside and the outside, I'm going to assume that the inside contains 0. So if you want to get a conformal welding that's singular with respect to Lebesgue measure, then you can make sure that the two harmonic measures are singular, mutually singular. And then in that case, you're going to get something that's very singular. So you're going to get a Borel subset of the unit circle that has full Lebesgue measure, but when you apply the conformal welding, you get something on the circle that has 0 Lebesgue measure. And why is that? Well, the idea is that if the two harmonic measures are mutually singular, then there is a set on the curve that has full harmonic measure from the outside, let's say, and 0 harmonic measure from the inside. And now if you look at the pre-image of that set under the map G, by conformal invariance of harmonic measure, it gives you a set on the unit circle that has full Lebesgue measure. So when you apply the map G to that set, you get something that has full harmonic measure. So it has 0 harmonic measure from the inside. So when you apply the inverse of F, you get something that has 0 Lebesgue measure on the circle. Okay? So just keep in mind this observation that whenever the harmonic measures on both sides are singular, then you have a singular conformal welding homomorphism in this sense. Okay, so now the question is, well, how do we obtain such curves? Well, here's an example. So if you look at the von Koch snowflake, for example, it's an example of a curve that has a property that the harmonic measures from both sides are mutually singular. The idea is that if you start a Brownian motion from the inside, well, if that Brownian motion is likely to hit a point from the inside, then it's not likely to hit the same point from the outside. That's roughly the idea why the harmonic measures from both sides are mutually singular. And then how does this property of singular harmonic measures relate to the geometry of the curve itself? Well, we have the following famous theorem of Bishop, Collison, Garnett, and Jones, who proved that the two harmonic measures from both sides of a curve are mutually singular if and only if the curve doesn't have too many tangent points. Okay? If and only if the set of tangent points of gamma has zero length, 0 one-dimensional Hausdorff measure. So that's an example of such a curve. And then you can expect that a lot of fractal curves should have this property as well, that the set of tangent points has 0 one-dimensional Hausdorff measure. Any question? No? Okay, so if we go back to the strategy now, so that's good. We explain how to get a singular conformal welding, But now what we want is we want to obtain these singular conformal weldings as part of a holomorphic motion. So in particular, we want a lot of them. So how can we do this? Well, for this, we're going to look at some Julia sets. So let me just briefly mention the basic definitions of Julia sets. So if you start with a quadratic polynomial z squared plus c, and then the field Julia set of the quadratic polynomial is a set of all complex numbers, such that if you look at the sequence of iterates, then it remains bounded. And then the Julia set is just the boundary of that field Julia set. And I'm also going to talk about the Mandelbrot set. So the Mandelbrot set is a set of parameters, so it lives in the parameter plane, and is a collection of all parameters for which the orbit of 0 under z squared plus c remains bounded. And another thing that we're going to consider is the main cardioid of the Mandelbrot set. So you can think of this as a set of all parameters for which the corresponding polynomial has an attracting fixed point. So maybe we can go back to the other screen I shared earlier, so this fractal software. So here is the Mandelbrot set. So here you have, if you look at a point in the Mandelbrot set, it's a parameter, and then it corresponds to a field Julia set that you see on the right. And then if you look at a point inside of the Mandelbrot set, then the Julia set is connected. And if you look at a point outside of the Mandelbrot set, then the Julia set is totally disconnected. So there is this dichotomy of Julia sets for quadratic polynomials. And now the component of the Mandelbrot set we're going to focus on is this main component here. That's the M0 that I denoted in the slides. And then if you look at M0, oops, sorry, I lost the Julia sets. How do we do this? Yeah. So if you look at the main component here, then we see that the Julia sets are Jordan curves. They're actually quasicircles, if you know what a quasicircle is. And then another thing that we're going to use is that the main component of the Mandelbrot set contain a disk at the origin of radius small enough, of radius exactly 1/4 in this case. And then if you look at the origin, then the corresponding Julia set is just a unit circle. Okay. So let's go back to the slides. There it is. So like I said, the disk centered at the origin of radius 1/4 is contained in the main cardioid of the Mandelbrot set. And then if you look at a parameter in the main cardioid, then the corresponding Julia set is a Jordan curve. Okay. So now what I would like to do is look at the conformal weldings of these Jordan curve Julia sets. Okay. And I would like these conformal weldings to be singular with respect to Lebesgue measure. And as we saw, this is related to harmonic measures from both sides being singular, mutually singular. And by the Bishop, Collis, and Garnett-Jones theorem, this is related to the set of tangent points on the Julia set. And now there is an old theorem of Fatud, which tells us that if you look at parameters sufficiently small in modulus, but not equal to 0, obviously, then the corresponding quasicircle Julia set has no tangent point. So here, this lambda over 4 is just a normalization to make sure that if you start with lambda in the disk and then you divide by 4, then you get something in the main cardioid of the Mandelbrot set. So it's some kind of annoying normalization that we have to carry around. And then if you denote by, let's say, h lambda, the conformal welding homomorphism of this quasicircle Julia set, then we get, as a consequence of what we discussed, that for all lambda small enough but not equal to 0, there is a Borel set that lives on the unit circle with full Lebesgue measure, but when you apply the conformal welding homomorphism, it has 0 normalized Lebesgue measure. And now you can, if you want, you can use a very standard argument by showing that if you take countably many values of lambda, then for each value of lambda, you get one of these Borel sets. Then you can take the intersection of these Borel sets. It will still have full Lebesgue measure on the circle, and you get the following. So there exists a compact set E that has positive Lebesgue measure, but when you apply all of these conformal weldings to the set E, you get something that has 0 Lebesgue measure. So that is almost what we want. The only thing that remains is to show that these conformal weldings are indeed part of some holomorphic motion. And that's the more technical part of the talk. So let me try to explain how we do this. Well, the first thing to mention is that if you want the conformal weldings to sort of vary holomorphically with lambda, then you should at least make sure that the curve vary holomorphically with lambda. Unfortunately, this is true in our case, and there is a holomorphic motion of those quasicircle Julia sets. So I call this the Böttcher, well, not I call it, probably it's called, I think, the Böttcher motion. So first of all, if you start with a parameter in the Mandelbrot set, then you can look at the Julia set. It's a Jordan curve. So you can look at the exterior of that Jordan curve. It's a simply connected domain. And then there is a conformal map from the outside of the closed unit disk to the exterior of the Jordan curve, the complement of the field Julia set. And you can always find a conformal map with this normalization, and with this normalization, the map is unique. And it's called the Böttcher map for this this quadratic, this parameter in the main coordinate of the Mandelbrot set. And now it's a standard fact that the Böttcher map is actually holomorphic in both variables, parameter, and also the variable z. So if you look at the following map defined on the product of the unit disk with the complement of the closed unit disk, then you get a holomorphic motion. So again, we have this lambda over 4 to make sure that if you start in the disk, you divide by 4, you get something in the main cardioid of the Mandelbrot set. So that gives you a holomorphic motion. And now you can extend this holomorphic motion to the whole sphere by Sladkowski theorem. Okay? So that's what I call the Böttcher motion. And then it has a property, it's a special motion, so it has a property that if you fix lambda, then the map G lambda is conformal outside of the closed unit disk. And it maps the outside of the closed unit disk conformally onto the outside of the Julia set J lambda over 4, the unbounded complementary component of that quasicircle Julia set. Okay, so that gives us a holomorphic motion of the Riemann maps on the outside to the exterior of the Jordan curve Julia set. But now what we want is a holomorphic motion that gives us the welding. So we should try to construct the interior Riemann maps also in some holomorphic way. And for this, I need to say a few words about quasiconformal mapping. So I'm going to keep this very brief. So roughly, quasiconformal mappings are some kind of generalization of conformal mappings where the map is allowed to distort angles, but only up to a bounded factor. So they offer more flexibility in practice than conformal mappings. So the definition is the following. You start with two domains, U and V in the Riemann sphere, and then you look at an orientation preserving homomorphism from U to V. This homomorphism is called quasiconformal. So first of all, there is a sub-LF condition. Don't bother too much with this. And then it needs to satisfy the so-called Beltrami partial differential equation. So the partial derivative of f with respect to z bar should be equal to some function mu times the partial derivative of f with respect to z. And this function mu is a measurable function on u, and we want its L infinity norm to be strictly less than 1. So that's an elliptic partial differential equation. So that's the definition of a quasiconformal mapping. And now if you look at this function mu, so every quasiconformal mapping corresponds to one of these function mu in the Beltrami equation, and this we call the Beltrami coefficient of the quasiconformal mapping. And you can think of Beltrami coefficient as some kind of measure of non-conformality of the map. So if you have a conformal map analytic, then the Cauchy-Riemann equations tell us that the z-bar derivative is 0, so you get coefficient 0 in that case. And conversely, if you have a quasiconformal mapping that has coefficient equal to 0 almost everywhere, then the map is in fact conformal. That's usually referred to as Weil lemma. Okay, so now that's pretty much all I wanted to say about the definition of quasiconformal mappings, but let me mention one of the most important results in the theory, the so-called measurable Riemann mapping theorem. So if we go back to the definition, then we have that every quasi-conformal mapping corresponds to a Beltrami coefficient. That's a measurable function whose norm is less than 1. And it turns out that this correspondence is in fact surjective. So that's the measurable Riemann mapping theorem. And it tells us that if you start with any coefficient that has norm less than 1, then you can always solve the Beltrami differential equation to get a quasi-conformal mapping whose coefficient is equal to mu almost everywhere. And moreover, we also have a uniqueness statement that this map, this solution to the Beltrami equation, is always unique up to composition by a conformal map. Okay, so let's go back to holomorphic motions now. It turns out that there's a very strong relationship between holomorphic motions and quasi-conformal mappings. And maybe a good way to state this is the following. So if you start with a map H from the product of the disk to the Riemann sphere into the sphere, then the following are equivalent. So that's a theorem that I wrote Burrs and Royden, but it's actually due to many different people. So the following are equivalent. The map H is a holomorphic motion. And then we have that the maps H lambda have the following properties. So for H lambda is a quasi-conformal homomorphism of the sphere. Its coefficient and norm is bounded by the modulus of lambda. Also, the map H0 is the identity. That's always the case for a holomorphic motion. And then an important thing to notice is that if you have a holomorphic motion, then the coefficients of these quasi-conformal mappings, they vary holomorphically with respect to lambda. And that's an if and only if. So if you have a collection of quasi-conformal mappings parametrized by lambda, which satisfies the following, then it is a holomorphic motion. Okay, so now let's see what this tells us about the Böttcher motion. So recall that the Böttcher motion has the following property. So if you take lambda in the disk, then the map G lambda is conformal outside of the closed unit disk, and it maps the outside of the closed unit disk conformally onto the unbounded complementary component of this quasicircle Julia set. Now we can apply the Burrs-Royden theorem to deduce that each G lambda is actually conformal on the whole Riemann sphere, and it satisfies the following inequality for the Beltrami coefficient. And also, if you look at how these coefficients vary with respect to lambda, then it varies in a holomorphic way. So this function is holomorphic on a unit disk. And that's how you see that the Julia sets, if we go back to the picture, so if you look at the Julia sets in the main cardioids, they're very closely related to each other. They're related to each other by a quasi-conformal mapping. So if you look at any Julia set in the main cardioid, it's the image of the unit circle, the Julia set with lambda equal to 0, by some quasi-conformal mapping. Okay? So it's called a quasicircle, and quasicircles never have, they don't have cusps. But as you approach, let's say, a point on the boundary of the Mandelbrot set, like 1/4, then you see that you start having cusps, and the Julia set is no longer a quasicircle. So you lose your holomorphic motion as you leave the main cardioid of the Mandelbrot set. Okay, so let's go back to the slides. Okay, so we have this about the Böttcher motion. And now the question is, can we somehow use this to construct the holomorphic motion that we want? The holomorphic motion such that the restriction of H lambda to the unit circle is the conformal welding of a quasicircle Julia set. And then if we can do this, basically, we're done. So how do we do this? Well, there's a little trick we can do using the measurable Riemann mapping theorem. So the idea is to start with the Beltrami coefficient of this map G lambda, and then you define a new Beltrami coefficient on the whole sphere. So basically what you do is you take the restriction of mu of the coefficient of G lambda to the unit disk, and then you reflect it across the unit circle, but in a sort of invariant way for the Beltrami equation. And then if you, this is another Beltrami coefficient, so you can solve the Beltrami equation, you get a quasi-conformal mapping. It's going to be unique if you normalize it so that it fixes 0, 1, and infinity. And then the Beltrami coefficient is equal to nu lambda almost everywhere. And now I claim that the maps H lambda have the following property. So the first thing to observe is that they map the unit disk onto itself, at least if you have a real parameter lambda. And that's basically why we chose this formula here. So that's precisely the formula you need to put in order to get a Böttcher equation that's symmetric with respect to the unit circle, so that when you solve the Böttcher equation, you get a function that's symmetric with respect to the unit circle. And it maps infinity to infinity, 0 to 0, so it has to map the unit disk onto itself. So that's the first property. And then the second property is that if you look at the restriction of H lambda to the unit circle, at least for real lambda, this is indeed the conformal welding of this quasicircle Julia set that we consider. And the reason, that's basically a simple exercise using the uniqueness part of the measurable Riemann mapping theorem. So if you look at the coefficient of H lambda and the coefficient of G lambda on the unit disk, they are equal. So then you can apply the uniqueness part of the theorem to deduce that this here has to be a conformal map. And H lambda maps the disk onto itself, so this is going to map the disk. So when you apply H lambda inverse to the disk, you get the disk. And when you apply G lambda to the disk, you get the interior of the quasicircle Julia set. So G lambda maps the exterior of the disk to the exterior of the Julia set. So it has to map the interior of the disk to the interior of the Julia set. And then finally, these maps H lambda, they are part of a holomorphic motion. And that follows from the converse statement in the Böttcher-Royden theorem. So if you look at the Böttcher-Royden theorem, all these conditions here are satisfied for the maps H lambda, so we do get a holomorphic motion. Okay. When lambda is equal to 0, G0 is the identity, so the map H0 is also going to be the identity. If you look at the behavior of the coefficient of H lambda as a function of lambda, it's holomorphic. That's why we put a conjugate to lambda here and then another conjugate outside. So that gives you a coefficient that varies holomorphically with lambda. And then it satisfies the same inequality as the maps, as the coefficients for the maps G lambda. So that's how you get your holomorphic motion. Okay, so I'm almost done. Let me just summarize what we proved. So what we proved essentially is that if you take any sequence lambda n in the unit disk, real numbers sufficiently small that converge to 0, then what you can do is you can look at these quasicircles Julia sets. You can define a map in this way using the previous slide, and that gives you a holomorphic motion. And the restriction of that holomorphic motion to the unit circle is the conformal welding of these quasicircles Julia set. And now you know by combining Fatou's theorem and also the Bishop, Collis, and Garnett and Jones theorem that the harmonic measures on both sides of these Julia set are mutually singular. And now this implies by the observation we did that there's a compact set that has positive length on the circle, but when you take the image of the set under these maps H lambda n, that gives you a compact set on the unit circle that has 0 length. Okay? And now this implies, so we have subsets of the unit circle, so we know that positive capacity is the same thing as positive length. So it gives us what we want. So the function analytic capacity is not continuous at the origin. Okay, so I think that's all I wanted to say today. So thank you very much.
Bravo, Malik.
Merci.
Can I ask a question?
Yes.
You talked about analytic capacity. Are there also related results on continuous analytic capacity?
Let's see. Oh, that's a good question. I don't know. Yeah, I'll have to think about this. That's a good question. Yeah, the same example is not going to work because these are analytic capacity, continuous analytic capacity can be positive for, can be 0 for sets that are connected. So I'm not sure. Yeah, good question. Thank you.
Malik, can I ask a fairly naive question? You looked in the beginning, you were saying that if you have a holomorphic motion, you define some real valued function of the set, and then that real function moves nicely, has some nice behavior. Can you look at complex valued function of a set?
Yes, I suppose you could look at any types. Yeah, you could also look at complex valued functions. I think in the results that I mentioned, they're all real valued. That's why I chose real valued. But yes, indeed, you could look at complex valued functions and then try to study the same kind of question for various complex valued functions f. Yes.
Okay, thank you.
I don't know of any result of this type though when you have a complex valued function.
Yeah, I don't. Well, I'm not sure if, like in multifractal analysis or somewhere, if something interesting
yes.
comes up, but I don't know. Are there any other questions? There is a question typed more regularity for Hausdorff dimension in the chat room.
Yeah, so in general, I'm not sure what is the optimal regularity, but what I know is that if you look, for instance, as Julia sets in a hyperbolic component of the Mandelbrot set, as we did, then the Hausdorff dimension varies in a real analytic way. That's a result that I think follows from this thermodynamic formalism in Ruel and Bowen formula and stuff like that. In general, though, if you have a general holomorphic motion, then the Hausdorff dimension need not vary in a real analytic way. I believe there's a counterexample looking at Hausdorff dimension of limit sets of Pushkin groups. There's probably a paper by Astala and Zinsmeister on this.
And one also question, maybe a little naive. I remember that Hausdorff dimension of the limit set for like a Fuchsian group, it may not be continuous, but it could be lower semi-continuous, right? At least in some cases. Can you say anything like this here, or this is, I may be completely wrong, I'm not 100% sure.
Yeah, so for analytic capacity, I think it's always upper semi-continuous because there's a result about the analytic capacity of a decreasing sequence of sets, and I think you can see from this that it's always upper semi-continuous. So the example we constructed is not lower semi-continuous.
There is another question in the chat from Murat. Can this result be generalized to nonlinear capacity like P capacity?
Yeah, that I don't know. That's a good question. Yeah, we really use this relationship between analytic capacity and Hausdorff, one-dimensional Hausdorff measure. There's also yeah, maybe I should mention that if you look at the theorem, at least for logarithmic capacity, the fact that it varies continuously, then there is a very recent result of Stamatis Poulias to prove the same result for condenser capacity. So that's another capacity that we know vary continuously under holomorphic motion, using essentially the same kind of method as in this theorem. Other questions?
Well, if there are no further questions, let's thank Malik again.
Thank you, everyone, and I hope you stay safe.